muy motivadas. Y a veces se están sentando sin llamarles.
Ya está. Estamos en el aire.
Voy a ver si hay alguien fuera para...
Vale. Estás ya en YouTube, ¿vale?
Vienen aquí con 6 personas que estaban fuera. Bueno, no sé si vienen.
No vienen.
No.
¿Castellano o inglés? English or Spanish? No, yo me prefiero hablar en castellano, español. English. Okay, thank you for coming. The title of the talk is Complex Systems, Giorgio Parisi's Nobel Prize in Physics in 2021. Last time I talked here, I think it was last time, I talked also about the Nobel Prize or in condensed matter physics about topological transformations, phase transitions, and topological materials. I think that was 2017 or 18. Also the Nobel Prize, and now I've been asked to suggest to talk about this Nobel Prize. This Nobel Prize was about for the groundbreaking contributions to our understanding of complex systems, and it was given to Manabe, Hasselmann, and Palisi. Palisi shared half of the prize, and the other two guys shared the other half. This prize is a little different from usual, I think, in Nobel Prize, because it's more it's not a Nobel Prize for a concrete or specific discovery, but for an area of research, specifically complex systems. In particular, Manabe and Hasselmann, whose work I don't know very much. It's about the physics or the modeling, mathematical modeling of climate change and the global warming. I hope the climate group will talk about this a little bit more in more detail, but I will concentrate in the second part of the Nobel Prize, which is for Giorgio Parisi, for the discovery of the interplay of disorder and fluctuations in physical systems, and then the poetic part of from atomic to planetary scales, which I don't know what it means. But actually, I think I understand the first part, for the discovery of the interplay between disorder and fluctuations in physical systems. So I will concentrate in this part of the prize, and let me start trying to explain why I think well, the talk is about why we think why I think the Nobel Prize is deserved, and what are the contributions of Parisi in this specific area of research. Those of you who know quantum field theory will know Parisi as well, because he started as a theoretician in quantum field theory. He made some important papers there for some years, and then he moved to a statistical field theory, so statistical mechanics, and made very important discoveries, like the one that ended in the Nobel Prize. And I will concentrate in that part. Okay, I will not talk about any of his work on quantum chromodynamics or interactions in particle physics. So the first, I would like to introduce you to fluctuations and disorder. What is the difference in physics between fluctuations and disorder? So fluctuations, when we refer to fluctuations in macroscopic systems, what we have in mind is thermal fluctuations. So fluctuations that are due to the interaction with a bath, a thermal bath. How we describe these systems in physics? Well, this is a fast course on statistical mechanics. You have a Hamiltonian with some degrees of freedom, so we will call sigma here. These degrees of freedom are from 1 to n, where n tends to be a very large number. We have many particles, many spins, or many something, and that is always the thermodynamic limit is the interesting point, interesting part. And in statistical mechanics, we know that the probability of a given configuration, so that the system has a certain specific values of the degrees of freedom, is proportional to this Boltzmann factor. Okay, where the temperature plays a role here. So the higher the temperature, the less important is the energy involved in the system, in the interactions, to define what is the probability of the state. And the lower the temperature, more important is the energy in this competition between temperature. How we compute things? We have to compute the free energy, which is the log of this thing. This is the partition function, which is not interesting here. The point is that we have to minimize something, and that something is the free energy. The ground state of the system, when we have thermal fluctuations or any kind of fluctuation, also quantum fluctuations, is the minimum of something. The ground state minimizes something. In statistical mechanics, is the free energy. And the free energy, this defines the state where the system will tend in the equilibrium. What is quench disorder, or what is disorder in physical systems? Typically, we have some added parameters to the Hamiltonian. The couplings of your Hamiltonian are random variables. That's where I use this J here, this vector that summarizes all the parameters of your system. And in this case, instead of being constant, these are random, but quench random. That means another realization of the system will have different parameters, but the parameters don't change in time or don't change during your experiment. Again, in principle, statistical mechanics is also able to give you the solution to this problem by the same procedure. We have the probability of a state for a given configuration of the disorder, for a given realization, and we have the free energy, in this case, is an average over that disorder. And the ground state again is a minimum of something, and that something is the average of the free energy over the disorder. So you see here the J is it goes out because you already have made an average over the distribution of J, and this is quench disorder. So this is the difference, and this is the terms the Nobel Prize referred to when it says interplay between disorder and fluctuations. Well, this is fluctuations, and this is disorder. Disorder, as I said here, typically is given, it enters in the Hamiltonian, but it doesn't have to be always like this. You can have also disorder that is effectively self-generated in the system. Suppose you have a Hamiltonian with some potential, some interactions, it doesn't of any nature, any kind, but these interactions are very slow compared with the time scales of these interactions are very slow compared with the dynamics of your system, of the particles, of the degrees of freedom of your system. In that case, for a certain scale of time, your potential can be seen as disorder because every particle sees a different environment around it. So the potential that every particle sees is not averaged in time. For instance, it can happen in Lennard-Jones potentials or even in gravity. So at low temperature, you have some quasi-static configuration of the system, so almost static, where each particle is a different and disordered environment around itself. So this is also some sort of disordered system. In fact, this is what in condensed matter is called a structural glass, so a glass. So a real glass from the point of view of the solid state physics. So it's just like like a window glass.
Can I just have a question? When you have disorder where you have to always have a change in the Hamiltonian, or you may have disorder not affecting this?
No, you always have the in this situation you always have disorder in the sense that another sample of your system will have different couplings, or in other words, you have a subsample of your system and you have some values of J of your couplings. And then you increase your system size and you can have different values of those couplings. In the limit of large systems, you expect, otherwise you would not be able to do anything, that things self-average, in the sense that you will have, in the thermodynamic limit, you are scanning, is making a scan or checking all the probability of possibilities for your couplings. All right. I don't know if I explained correctly.
I'm just curious. Whenever you have a disorder, you have a different energy for a different.
Yes, for a different. You have a different Hamiltonian.
Okay.
And then your configurations will change. Actually, they will rearrange differently in different disorders. That's the complexity of the problem. So this is, yes, you have. So this Hamiltonian is actually right. You have a distribution of Hamiltonians because of this J. Even if you don't have thermal fluctuations, you will have a distribution of Hamiltonians. I don't know if I explained correctly. I explained one question, but let's go on. I think to understand what the contributions of Parisi were, you have to understand a little bit about magnetic systems. It's very interesting how magnetic systems are at the beginning of this story. And then in the end, magnetic systems are really not the most important part, but actually it's where the motivation and ideas were generated. So I think you need to understand a little bit how a magnetic system works, a simple magnetic systems, to understand what the ideas of Palisi were that were really made a breakthrough in the field. Let's consider the most simple interactive system that you can think of, which is called the Ising model. It was formulated in 1920, in the era of quantum physics. And it's a very simple model where you have spin variables, sigma I, that contain values +1 or -1. In a regular lattice. It's typically a square lattice. This is an example of the Ising model in a square lattice, with the spins pointing up or down randomly. The Ising model considers the simplest interaction Hamiltonian you can think of in physics. So there is nothing more simple that can be simpler than this Hamiltonian. You only consider that your binary variables, so discrete binary variables, interact with nearest neighbors. Each spin interacts with the spins that are in the coordinates, nearest coordinates in the network. So in the square lattice, you have every spin has 4 neighbors, and this is what is meant by this angle that the sum runs over neighbors, and you only have one-to-one interactions. Right? This is the simplest Hamiltonian you can think of that takes into account any kind of interaction in a physical system. Well, this simple Hamiltonian is enough to explain magnetism in a quite a wide range of materials. Dj is the coupling, is the intensity of the coupling between the tendency of one spin to affect or interact with the neighboring spins. Okay, this is Dj. If J is positive, we have a ferromagnetic behavior. That means that the spins tend or prefer to be aligned in the same direction. At low temperature, we will have that the spins prefer to be pointing in the same direction. If J is negative, we have antiferromagnetic behavior, so that the spins tend to have opposite sign. At high temperatures, the details of this interaction are not important because you have much thermal energy, so that the interaction energy can be is negligible. In the end, you have random spins, orientational spins. When you lower the temperature, or in the limit of low temperatures, then this is relevant. The spins will turn, you don't have enough thermal energy to compete with this interaction, and then this interaction will produce the ordering of your system. So the system will spontaneously get ordered. In fact, this is the typical phase diagram of a ferromagnet. As I said here, in any case, the ground state, so the minimum energy of the system, the configuration where the system goes, at low temperature is always an ordered state. What do we mean by an ordered state? Well, as I said here, that all spins point up or down, or opposite signs in the case of an antiferromagnet. Let's concentrate by now in the ferromagnetic case. If I compute the total magnetization per spin in my system, then this magnetization you can compute, or you can see that it's at high temperatures is 0. The system is completely, the spins are pointing randomly, so the sum over n being very large, it's going to be almost on average 0. And at low temperatures, this magnetization will get a finite value. There is a point in between where a phase transition occurs between the disorder and the ordered state. You can see this also in terms of energy. If you compute the energy, free energy I was talking before, at high temperatures you have this free energy. So if you compute, you do the maths, you will free energy that is like this, with one minimum here. And here is where the system will go. This minimum corresponds to a magnetization equal to 0. So this is at high temperatures. Then at low temperatures, this minimum splits in two, and the free energy has two minima. And the form it takes is like this. This is actually this is a t equals 0, and you have this free energy with two minima, where the system will go either to positive or negative magnetization. This is second order phase transition, so this simple interaction already takes is able to explain, or it's able to sustain a spontaneous symmetry breaking, which is this fact that the state of the system is a state that is not maintaining the symmetries of your system. You have of your Hamiltonian, sorry. You have a scale invariance, critical exponents, lots of interesting effects, and ergodicity breaking, which is the key point to understand what is coming. Ergodicity breaking means that our temporal average in our system do not coincide with average of the states over the states probability. What happens is, if I have my system in this temperature and I start for any random configuration, I start, say, a simulation or an experiment, the system will spontaneously pick up either a positive or a negative magnetization. So if the system, once we start with, say, average magnetization of 0, the system will spontaneously go either to minus or to a positive magnetization, to any or to one of these branches, and it will not move from there. So if you do an average of your magnetization, if you want to compute the magnetization and do an experiment, you obtain a finite value of the magnetization. However, if you average over the ensemble of possibilities, your magnetization is 0. So this is what we call a ergodicity breaking. The system gets into a minimum, and the minimum is so profound that it cannot jump to the others. If this valley, if this mountain is low, thermal fluctuations will allow the system to turn the magnetization from plus to minus globally. even in the ordered state. But in the thermodynamic limit, this barrier is infinite. So the system will actually remain in one of the values. This is a ergodicity break. The point here in this simple system is that these two equivalent, because they are equiprobable, another concept that is very important, these two states are equally probable, have the same probability to occur. These ground states can be connected through a symmetry transformation. So you have your system here. If you flip all the spins, your system will be in the other side. So the two systems are somehow equivalent in probability, and they can be transformed one in each other through a symmetry transformation. And also, very important from the experimental point of view, the ground state, this ground state I'm talking about in the low temperature phase, can be selected by the experimentalist by applying some external field. If I consider the same Hamiltonian and then I add an external magnetic field, intuitively, you don't need a equation. Suppose you have your system, and your system is at this temperature, it has magnetization 0, and it has to evolve. So it has to go either this way or this way. You can select which of the states the system will go just by adding a small kick at the beginning in one of those two possible states. Either you have some magnetic field or you add some negative magnetic field, a small one, even a small infinitesimal amount of field is enough to invite the system to roll down one of the slopes instead of the other. So the experimentalist can actually decide what the two states are selected by the system. So this is, well, this was all very well known in the 40s and 50s and in the 70s. That is when Palisi made his in the 70s. This was exactly known by means of randomization group calculations. Okay, this is not only intuitive, but it only can be computed exactly for this Einstein model. However, there are other interesting situations. As you see here, this system has no disorder, it's a crystal, but there are experimental situations where you have disordered materials. So there are some metallic alloys where you put some in some metal that is not magnetic, you put some, replace some of the vertex by a magnetic material. Más bien no, ¿no? Well, metallic alloys. You have some bulk of a metal which is not metallic, and you replace some of the atoms of that metal by another metal which is metallic. So it's the difference between having a crystal of metallic atoms and having something like this. This is disorder. So the distances between your magnetic nodes or atoms, spins, will be random. It's randomly placed. So this is what we call a spin glass. In this case, as you see, there's a big difference with this situation. Here, the crystal, this is the case we have been describing, and in this case, interactions will be random because every side will see a different environment of magnetic particles. And the distances are also random. The distances between these spins or these magnets are also random. So the interaction, the J, will be also different depending on which spin we are looking at. So this is what we call a spin glass. So this is what drove the theoretical analysis of this kind of systems. And there were experiments on this type of metallic alloys already in the 60s and in the 70s. In 75, there was the first model, very simplified. Say it's like I just consider the Ising model in a random environment, and it was the Anderson model. Anderson is the same Anderson that received the Nobel Prize for the localization in random media, by the way. He also worked on he also came from high energy physics. In 1975, they proposed this model. This model, as you see, is just a obvious generalization to include disorder in the Ising model. Okay, instead of a crystal with constant J, I put the interactions that depend on the position, and these interactions are distributed randomly. So by construction, I suppose that these J are random variables. Say Gaussian, it doesn't matter what the distribution is as far as it's well behaved, but Gaussian allows you to make calculations. So a Gaussian random variables that are coincident. That means they don't change in time, but they are distributed. So you have to run different samples of your system and average, and you have spins. And the interesting point of these J's is that they are generalized to the cases where you have mixing ferromagnetic and antiferromagnetic systems. So you can have metallic alloys where you are mixing atoms that tend to be ferromagnetic with atoms that tend to be antiferromagnetic. So you have some interactions are, say, positive and some are negative. What is the importance of this? Frustration. This is a main ingredient of all this kind of system, or magnetic systems, that then will be extrapolated to other kind of systems that are non-magnetic when I talk about the more general settings of complex systems. Frustration. What is frustration? Well, as I said, the interaction tend to equalize spins, orientations of spins in a local environment. Okay. In the case of the ferromagnet, it's 4 spins that are in a minimum, in a ground state. They are comfortable because they are satisfying the requirement of being minimal energy with all the neighbors. So this is the ground state for the ferromagnet of 4 spins, 4 neighboring spins. However, when I have disorder, suppose you have one of these positive interactions becomes negative, antiferromagnetic, then there is frustration. What means frustration? Frustration means that I cannot get a configuration that is comfortable, or there are many ways to be to have minimum energy, but some of the spins are frustrated. They cannot be in the minimum energy state that they would prefer to. Suppose this is positive, and then this positive interaction makes this positive, and then this negative interaction makes this negative. When I get here, since this is a positive interaction, this spin will prefer to be down, but because of this positive interaction with the other neighbor that also wants to be down, it cannot be, it doesn't have any non-frustrating situation. The result of this frustration is that you will have in this kind of system very many ground states. But in this case, you have only 4 spins. You only have, I think, 4 states. But this multiplies when you have many a macroscopic system. You will have very many ground states with very similar energy but different, and where the system feels okay, and because of frustration, it's difficult to change from one state to the other. This is the local minimum. So this is the picture that one of these disordered materials will have. This is the free energy, or the energy that you want to minimize. I recall you in this is the energy for the Ising system with no disorder, and this is what happens when you include disorder. This is for one disorder configuration, you have this landscape of energies, very complex with very many local minima. And this is what you see here is a sketch, obviously, of the energy versus the configuration. Different configurations of your system, different arrangements of spins will have different minima, minimum of energy. All of them are minimum of the free energy. So it's difficult to decide for the system which of the minima to stay. And very importantly, these are ergodicity breaking as well. Same exactly as the INSI model, these minima are ergodicity breaking. That means once the system gets in one of these, it's very difficult for the system to go to explore the rest of the minima. There are no mechanisms in the thermodynamic limit at low temperatures to visit other minima. So it stays in one of them. It cannot be the best. It cannot be, maybe no, it's not the most the smallest energy, but it's where it has to stay. Yes.
So, in the situation where you verify, well, this is, I understand it, is that the system is not going to be able to be in all the possible available systems. But then, if you are in this situation, then the Boltzmann factor doesn't make sense. That will give you the probability, right? So, how could it be that the free energy system is defined if you don't have a Boltzmann factor? You don't have
I will. I think you can. I prefer you ask this after I continue, when I finish, okay? Because I will talk a little bit about this. But you understand this, all right? You have a given set of a given disorder, a given J. Okay, and you have this is the what your system energy space looks like for different configurations. The point is that when you start an experiment, your system will go always tend to go to a minimum. Once it's inside one of these minimum, it's very difficult for the system to visit others. It's very unlikely that you get the best minimum, okay? The best minimum. So egolicity breaking, as with the Ising problem in the crystal, in the non-disordered case, but there are important differences. As I said, there are many ground states exist, not only 2, not only 4, but many, exponentially many. Where the system remains for a very long time. In the thermodynamic limit, in a real macroscopic system, this time is infinite. That's why the egolicity is broken. And these pure states, these ground states, are not connected through any symmetry. So there is no way for an experimentalist, so speaking in the same terms as I said before, for the experimentalist to say, no, I want to go, there is no known way, there's no way because there is no simple symmetry connecting this minima. So you can say, no, I don't want to go to that ground state, I prefer that one for whatever application I want to do. Okay. And this is, in fact, this is the key of problem of this kind of system from the, say, application and computational point of view. In principle, what we have to do is to compute where the minima of this function are. This function is the average over all the disorder configurations of the free energy, and that amounts to compute this thing. This thing is terrible to compute. This average of the partition of any function over a distribution is very difficult to offer. The logarithm of a random function is very difficult to do. As I said, this is the key of the problem. I have to compute this. That means I have to compute the average of a logarithm of something. And the problem, if you are tempted to do this, is not possible to do. The average of the logarithm is never equal, not even similar to the logarithm of the average. Right? This is a typical error. So this is mathematically a very difficult problem. And this was there for some time. The problem, how to compute, to reproduce experiments in disorder magnetic systems. Let me just explain what this was the idea of Palisi to solve this problem. Not only this problem, but many, a group of problems in the same category. Basically, how to solve something like this. So it was a technical problem. But in the end, by solving this technical problem, he solved lots of physical problems in applications. Okay, I will briefly discuss later. The idea of Palisi was the following. I will take in the logarithm this expression. This expression is an analytic expression in mathematics that you can express the log of x, like the limit when n tends to 0 of x to n minus 1 divided by n. You can check this by doing 2 lines of algebra. You can convince yourself that this is true. So the idea that's called the replica trick is the following. What I will do is I have to compute this, all right? So I use this. I compute instead of this average, I consider x now is z, and then I do the log of z is set to the n, minus 1 divided by n. I take the average, and the average of all this is just the average of this. And set to the n, the average of set to the n is something that in statistical mechanics, at this, we think we can compute, or at least try to. It's not the logarithm of something. It's the set to the n. It has some hopes. I mean, it gives you hopes that you can make calculations. So that's what Palisi did. And you have to compute something that is looks very nasty, but it is nasty, but you can do, okay? Then what we do, that's what is called the replica trick. What we do actually by doing this is to replicate the system n times. This is your system replicated n copies of your system, and compute everything as a function of n. Okay, I can do this as I do. If you remember your statistical mechanics, this is what you do when you solve the ideal gas case with no interactions. You can do something like this. Every particle has its partition function, and the partition function of the whole thing is set to the n, where n is the number of particles. This is a standard technique in with the particularity or the difficulty here that you have here this average over this shape. But that's how you work typically. So what the idea of Paris is to replicate the system n times, as I said, and after doing all the calculations, the principles you can do in statistical mechanics, where G is fixed until you do this average. That's why the system is a replicate, is replicated n times, because all these n factors have the same disorder. After you do the calculation, then you take the average. And then finally, you take the limit n to 0. This limit n to 0. And why this is called a trick instead of a technique? Well, because this n is supposed to be, say, the limit n goes to 0. Here is supposed to be, there's a conflict here, and the limit n going to 0. In the sense that here n is the number of copies. But what is the sense of this when the number of copies of replicates goes to 0? So this for many years was a weakness of the procedure. That's what's typically called a trick, because it was seen as, yeah, well, this works, but it doesn't make any sense mathematically. Okay, it was true, and we'll say something more about this in the future. But he did this and just make the computations. Well, I skip this and made the computations in a, say, in a mean field version of the spin glass model I said before. And these are the two key papers where Parisi solved this problem, this replica trick, and what the solution of the disorder magnet is, of the glass, or what is called a spin glass, a glass of spins. These two papers, one is in 1999 and the other is in 1983. These two papers are the base of thousands of papers that were made with these ideas, not only in spin glass, but in many other areas. What are the conclusions of these papers? What he was able to prove, even with these jumps, mathematically not very well justified, like the n to 0 limit, he was able to make a computation, and this computation turned to be very good. At high temperatures, he was able to prove that the system is a disorder. There is an order parameter that takes the value 0 at high temperatures. And then at low temperatures, below some critical value that he could compute, the system shows or has infinitely many phases. It's characterized by a different value of this order parameter. I recall you, in the case of a crystal, of a perfect regular lattice, you have disorder phase high temperatures, lower temperature, you get a order phase, but you have only one value of your order parameter. Okay. In this kind of systems, you have infinitely many ground states, And each of those ground states is characterized by a value of the order parameter. All of them are living together. So you cannot tell from the start where the system is going to go, which of the minima the system is going to stay in the end. For the low temperature phase, the system stays at a ground state, a configuration with an order parameter Q that is random and is given by some probability that you can compute. This probability for the simple glass spin glass model that I've been discussing has this form. It has two deltas, say in the extremes, and then this distribution. What is the meaning of this? It means that you have infinite states, and every of these states has a probability to be chosen that is given by this P. This has a physical meaning because, say, we have a disorder phase and we have something below the glass phase, say, and we say it's not actually an order phase. It's not like because the system is still disordered. But you can prove, as I said, that there's an order parameters that tells you that something different is happening. Okay, you have this distribution of the order parameters, and this is why it's called the replica symmetry breaking. In principle, the replica are these copies, and the symmetry breaking refers to the fact that instead of having just one value of your order parameter, like in the ISIN or the crystals, you have many or values, possible values for the. So the symmetry between the copies of your system is broken, and your system gets a distribution of values for the order parameter. This was very, very unusual, very, very strange in physical terms and in mathematical terms. As I said, this was the contribution of Palisi in 1999 and 1983. And these are basically the two papers that have say justify the Nobel Prize. You could say, well, it doesn't seem to be for a Nobel Prize. Well, if it was only this, it's true. But what happened with the spin glasses? Actually, it's very funny. We'll say you cannot measure this in an experiment, in a spin glass, in a disordered magnetic system. You cannot measure this distribution. You cannot measure even this order parameter. It's an abstract quantity that you cannot measure in an experiment in magnetic system. What is interesting is that the Palisi was able to compute things that can be observable. If this happens, what happens to the correlation functions? What happens when I apply a field, a magnetic field, and I vary that field in time? What happens when I lower the temperature, I cool the system at a constant applied field? What happens, what is called the susceptibility, how the magnetization changes of my system when I change the external field? All these things that experimentalists measure every day, he was able to predict. And the amazing point was that these observations were checked by the experimentalists, okay, in the years after these two papers, in the 80s and early 90s. So experiment from the experimental point of view was a great achievement. But I think that the most important part was the concept of how this landscape is organized and this structure of minima, the effect of disorder on this structure of minima and the role of frustration. Actually, after a spin glass, in the end, it's only a paradigm of a complex system. This picture of the spin glass, of this simple model of the spin glass, in the end, it's just a paradigm of many other situations in physics and other disciplines where you have an effect of disorder competing with fluctuations, and you have the same kind of problems and the same kind of dynamics. I will mention a few that were, say, developed from or after or with ideas related with spin glasses, replica trick, or replicas. For instance, self-avoiding walks. A self-avoiding walk The volume walk is a polymer, okay, a long chain polymer, very long. And the sofa volume walk is, suppose you have here you have a medium with atoms, and then you have a polymer that starts to grow. So you have the seed here, a first atom, and then another atom adds here, then another atom adds here, and then this continues. The polymer cannot cross with itself, and it's in obviously it's in a closed environment, so it cannot just go away. It has to take very convoluted forms, so to continue growing with the constraint of the volume that is available in the system. In the case that that medium is disordered, so you have to do that in a porous media, for instance, or in a system where some kind of quantity disorder. This problem is related with the same problem as the spin glass. You have to confront exactly the same kind of problems. You have the infinite minima, the infinitely many minima on your system. Your system will get stuck in a configuration, and it's very difficult for the system to get in another configuration. This is a view of the polymer in 3D. There is an energy cost. It's very simple to write this. From this V is the disorder. This is the cost of the energetic cost every time you grow an atom. And if this function is random, it's quantity disorder, this problem is exactly the same. It's very related with the problem of the glass. The ground states of this system are paths, like this path, that minimize this energy. And if this is a disordered quantity, a quantity disorder, you have a problem to minimize this energy. There are infinitely many protein folding. Protein folding, as you know, proteins are typically very compact, very involved objects that curl on themselves and bend on themselves. Very typically, depending on temperature and conditions, they can form different structures with different. They open and then close again, etc. Well, the energy, or the free energy, or the Hamiltonian of those configurations is again a case of a quantity disorder problem, very similar to the spin glass. The only difference is that you have the spins, you have the positions of your atoms. What is the origin of the disorder here? Well, given a configuration, a folding of a protein, carbons, for instance, don't see the same environment. This carbon, another carbon, don't see the same environment, and that's the quantity disorder in that situation. So you can try to. This is a very important problem nowadays. How to predict the routes or the paths that the protein is going to follow in order to get from one minima, local minimum of the free energy, to other minimum. There is a competition between energy and entropy. For instance, sometimes you can prefer, I mean, the molecule will prefer to waste energy if entropically the final solution is it diminishes the free energy. So there is a competition between energy and entropy at a given temperature. And this is a problem very much related with the problems and the techniques that you use are Parisi's techniques as well. Replica and in computer science. Think of a physical system as we are always treating. Free energy is energy minus entropy times temperature. Okay. In a disordered medium, this is a problem we are dealing with all this time. Suppose I take 0 temperature, then the problem of minimizing F becomes an optimization problem. There is no more temperature, there is no more physical system as such, and I can take E to be anything. I can take E to be what I call energy, can be replaced by anything. Can be replaced, I mean, depending on the problem, it is replaced by different things. It can be a distance, it can be a price, it can be anything. The problem in the end is the same, in the sense that I have some quantity with some degrees of freedom, and there is some disorder. And I have to minimize, I have to find what is the configuration that minimizes the average of that quantity. That quantity is no longer an energy. There is no longer a temperature. There is no longer necessary interaction in physical terms. I don't have to take necessarily physical terms, physical systems. But the problem reduces to an optimization. There are many problems in computer science that are like this. And typically, in the presence of quench disorder, these optimization problems very often have NP problems, are non-polynomial problems in the sense of algorithmic complexity. That means you cannot find an algorithm in polynomial time that can solve your problem. Your problem is minimize this. Find the minimum, the configuration that minimize this. Examples. The salesman's problem. I think most of you probably have heard about this problem. The problem of the salesman's problem is a theoretical problem in which, given a list of cities and the distances, which are random or can be different, between each pair of cities, what is the shortest path route that visits each city exactly once and returns to the original city? This is the big cities in the States, as an example, but it can be, this is a configuration. I can have many other configurations, so the system is disordered. And you have to find what is the path that minimizes the distance. In this case, this optimization problem belongs to this kinds of problem where this A is the distance. And as I said before, this is known to be a non-polynomial, an NP problem in computational terms. Neuroscience and neural networks. A very popular model of neural networks, the Hopfield model, that allows you to memorize patterns, memorize words, binary words. If I have a system of n neurons, I can memorize a vector with n bits. That's an n bits word in that system. The Hopfield model works by what you have your, in this case, 5 neurons, and each neuron is connected with everyone else, right? With any other neuron, with some couplings. In the way I can introduce the solution, I want to memorize in the couplings. Okay? There's a technique that simply multiply the vector solution that you want to memorize in your couplings, and you have an update, a very simple update rule, in such a way, I don't want to go into details, but in such a way that these obviously are disordered couplings. This is what the disorder is, and you evolve this. Any configuration you start of your neurons, they will tend to recover the memory you have put it in, okay? In these couplings. From any given configuration, it will go to that effect. And again, it's a disordered system. If you change the couplings, you change your memory, and then you can start again. Once the memory is stored, the system recovers that state for any random configuration that you put the neurons on. There is an energy that is not an energy, but you can call it an energy. It's a quantity that you have to optimize, minimize. The trajectory of your system will minimize this quantity, and exactly the same as in the spin glass, the Hopfield model will tend to minimize this. The trajectory will try to minimize this initial configuration through this random couplings. As you see, well, the energy is very similar to the energy of the easy mode, just by chance. More about neuroscience. There are networks of fine rate networks, heterogeneous networks. When you have, this is dynamics of every network. This is the activity of the network in time. This is a typical time scale that the index I is different networks. Typically, you have n, where n is macroscopic, very many networks, very many neurons, and they are coupled to each other. Okay, this again is the coupling from neuron I to neuron J, and there's some nonlinear function that tells you what is the response of any neuron to the input. This dynamics is very simple. If you just imagine this is not here, you can see this will give you some. If there is no coupling, any initial state of your neurons will give you an exponential decay of x with time, okay, with some characteristic time. You remove this term, you only have an exponential decay. as soon as you include, you take into account couplings, so neurons communicate with each other and send the inputs one to each other, you have very rich dynamics. Again, you can define an energy function, an energy function. Here, energy has no sense. The system is dissipative. You don't have Hamiltonian, you don't have temperature. This is not a thermodynamic or mechanical system. But you can define this function, call it payoff function, call it as you wish, that you have to minimize. The trajectory of the system is determined by the trajectories that minimize this let's call energy. Again, with the random couplings, these quaint couplings between the neurons. You can have a plethora of dynamics in this kind of systems. Like, for instance, you have when the neurons spike, the neurons get activated and send a signal. You can have synchronization, like in this case. Here you have every neuron, and here you have time. If you see this in time, the neurons more or less put, say, they fire more or less in accord one with each other for the whole ensemble. Then they stay silent, and then fire again, then they stay silent, then fire again. And you can have all the kind of behaviors. You can have here, again, this is synchronization, this is neuron number from 0 to you have here 150 neurons here. You have a point when the neuron is firing, you have blank when the neuron is not firing. So this is time, and here you have synchronization again. The population is firing at the same time. There are other configurations where neurons fire for long times, but one independent of the other, like they are not connecting or talking to each other. And you can have also random situations where the neurons fire uniformly or randomly. As I said, this depends on the parameters of your system. It's a problem that actually is nowadays is research. It's not still is an unsolved question, and there are many questions how this is connected to experiments and how to this is actually a minimal model for the behavior, the macroscopic behavior of brains. Here I have flocking, swarming, forming in living systems and in robotics. Let me just, I think, okay. This is a typical example of a complex system. In this case, this belongs to the complex system, the case where the quench, the disorder is self-imposed in the system by the neighboring of every bird. Well, this happens with birds, with fish, as you know, with cattle. It's a typical example of one emergent complex behavior from a very simple behavioral system. Well, this can be described in the same terms as I've been talking about. Let me see. This is all right. So this is what's called flocking, swarming in the case of things that move in water typically, living systems, and in robotics. It's very probably you have seen this in TV or in YouTube, videos of experiments with many robots that behave like swarms or like birds in collectivity. This can be explained and can be predicted by statistical mechanics with the same tools I've been describing up to now. This is a paper published in the Proceedings of the National American Society, PNAS, statistical mechanics for neural flocks of birds. What these people did was to take experiments where they measured how these birds move, trajectories, and they tried to construct a model. The simplest model they could think of is a model inspired in spin glass. This is the dynamics of S is the vector vector velocity, the velocity vector for every bird. I goes to from 1 to n, where n is the number of birds. And you have here the dynamics, and the Hamiltonian is actually the spin glass Hamiltonian. Jij and SA, you have here, they haven't, if you see here, this H is the Hamiltonian of the spin glass problem. How they get these quaint random variables? They have adjusted the values of these numerical values from observations. They took observations, they ran many films of movies of these birds moving, all the trajectories, and what they did was from these motions, they derived correlations, and then what is the values of J, what is the distribution of values of couplings that I have to put here to best reproduce these correlations that I see in my observation. And then what they did is to go with these numbers that they were measuring experimentally, run a simulation and reproduce the results that they were seeing. So this was a way to explain or to justify that behind the movement murmurations, this is the name of these movements of the birds. These movements of the birds, there is a very simple glass-like model inspired in simply in the spin glass problem. I think this was my last. Okay, my last transparency, another application, optical systems. I didn't know about this before preparing this talk. I was really surprised. But you can have random lasers with quench disorder. I haven't read the paper, so please don't ask me. I just wanted, that's why it's my last transparency, because I was really surprised. The papers are very recent, and they are all I mean, they are very good papers in Nature. And the thing is that they use lasers in some kind of random or quench disorder configuration. Lasers, many lasers, I guess. The infant here, they call the glassy random laser, and they interact with each other, and they measure, I guess, the light, the amplitude, and then it's the first time I have seen that some experiments where real experiments in the lab where they are able to measure the distribution of the order parameter in this kind of systems. As I said, in magnetic systems, you cannot measure. You have to measure the implications if this distribution exists indirectly. But here, they were able to measure actually the order parameter and how it is distributed. I think it's, I mean, I want to read this because it's really amazing. As you say here, the equivalent to high temperature is this distribution where you have, say, an symmetric distribution of the order parameter around 0. If you go to the equivalent to the thermodynamic limit, in this case, it would be a delta. You only have the value 0 for your order parameter. Obviously, if you don't have infinite number of lasers, it will be somehow rounded, and you have this maximum. And then this is the symmetry breaking of the replica, where you have a distribution of the order parameters. So you have many states that are many ground states. All of them possible are not equipped with the same probability. They have different probability. And as I said, this is the peculiar and typical characterization of glasses. The experiments are in lasers. I think there is another one on this one. In disorder nonlinear wave propagation. So it's, I mean, I cannot say much, but I was impressed to see this distribution. So as my only intention here was, after the maps, try to show why, but to explain why Giorgio Parisi has received the Nobel Prize for, even if you can think, I mean, at first sight, these two papers are very technical. They partially solve a problem in a specific area of magnetic disorder systems. The thing is that these two papers, another paper he published after this, gave a an outburst of research in an all kind of systems, related, partially related, generalizations, etc., where the picture of the energy landscape, the minima, the periodicity breaking, and the replicas has been tremendously useful. It's a way to be able to compute, as I said from the beginning, to be able to compute the average of a logarithm that before 1979, no one was able to do, right? And this is vital in statistical mechanics, in computer science, as I discussed many problems related with this, about optimization, and in other branches of physics as well. So thank you, and you have questions? So I've been speaking English only for you, so I hope you have a question.
Yeah, I have one question.
Great.
So, you mentioned that the particular one's system, it can be possible that they can stay in a different local minimum possible state. So, is there any tunneling effect so that the one from particular local state can reach to another one? Because you mentioned it will stay there for a very long time, maybe for infinite. So, is there any possibility of tunneling?
The possibility of?
Tunneling from one particular way to another?
Well, tunneling, not because this is not quantum. I don't know. I think I read something about quantum spin glasses. I don't know what happens there. It's not tunneling. It's just a thermal activation. It's a Arrhenius typical classical activation. You have something lying down in a minimum, and if you have received an input of thermal energy, kT, a fluctuation that is enough to jump the barrier, you can visit another minimum. The point is, in finite systems, finite means a finite number of degrees of freedom. These barriers are finite in height. So you actually, in finite systems, you can jump from one minimum to one minimum to other. Okay. Same happens even in the crystal or order in this crystal case. You can jump from here to here as far as this barrier is low. The point is, in the thermodynamic limit, when n goes to infinity or when n goes high, this barrier grows with the exponential of the system size. So it doesn't matter n is not infinite. Say you have some macroscopic 10 to 23 particles in your system, Avogadro number, 1 mole, or okay, you have normal situation, 100 grams of water, then you don't have enough energy to jump because this barrier grows with the exponential of the degrees of exponentially with the degrees of freedom. And the same happens in disordered systems. The difference is you have, instead of just one barrier, you have many barriers of different disordered sizes, but all of them grow with the system size. So visiting some other place, some other minimum from the place you are is more unlikely the larger the system is. So in macroscopic situations, that doesn't happen. So you don't see the system traveling from one place to one minimum from. So it stays in one of the ergodic components are called. These components are dissociated one from each other as soon as the system works. And this is typical of all the systems I discussed, protein folding. Thanks to the fact that the proteins are not that large, they can unfold and change configuration. Otherwise, it wouldn't be possible.
I have another follow-up question. Maybe it's not relevant to this. So when you are storing some data in our device, so we generally store in our 0 or 1 or -1 in the identifier in that state. So if there is a kind of this tunneling, so with the thermal fluctuation, then whatever data we are saving, it will change after some time because of this fluctuation. So
That I guess that's why you don't use glass to store your information.
so that
You use a
data will
crystal.
be huge.
To store your memory, your magnetic memory is as good as you can a good magnetic lattice, no disorder. So you don't have impurity. I mean, you can have some. That's, I guess, a faulty device, but there might be some specifications on the quality of your hard disk, for instance, or your magnetic tape, so that the number of impurities, the disorder of your system is not larger than something. Otherwise, you will have problems. So obviously, yeah, you cannot store what you want. That's a good point, actually, because as I said, one of the key questions here is that the experimentalist can select the state, the configuration, whether it goes to one place to the other. Instead of to have thousands and thousands of minimum, it would be fantastic to be able to select your system to go to one place to the other, because you can use that system to store information. But it's from not only in practice, but also from a theoretical fundamental point of view, it's impossible to select. The selection is an NP problem. To select exactly and to decide an algorithm how to configure your state, how to operate over your system, so that the selected ground state is one specified one, it's a non-polynomial problem. So there is not only a problem, a practical problem, but it's a theoretical problem, a fundamental problem to use this information. You cannot reach, you do not have that information to be used.
So into the problem, so you have local minima which are not connected by fluctuations.
Yes.
So there are like isolated systems.
Ergodic components, yes.
Ergodic components. Okay, so for each of those, it's clear that you have a well-defined free energy. Okay, but then there is not a global free energy of the system because
Yes.
they are not connected.
Well, that's a very good question, and now I think I can answer with all the slides. This is one sample of your disorder. Suppose you do a trajectory and the system stays, say I don't know, here. It's not the best minimum, but it's the minimum it found. Then you change your configuration. That is no longer a minimum, and then the minimum is somewhere else, and then what you expect is in a macroscopic system that the average of over the disorder gives you the answer of the average result of your experiment. That's what you do always. Is the same that you do with temperature, is the same that you do with any kind of randomness. Otherwise, it could be that it's not the case. No, it could be, but then the physical system is not really. You don't want a theory for one disorder. You want the theory for disorder coming from certain distribution. So for all the cases, all the samples, say macroscopically, you expect that if you measure in bigger and bigger systems, your measurement will be closer and closer to the.
Okay, but this is an assumption, like the fundamental assumption of the mañanas.
I don't know. I cannot give you an answer. I will have. I mean, I would need to think. I understand your worries, but it's an assumption.
I think it is because it is related to the body. I mean, it's not related to the fact if the system is a body or not, because it's not the difference between.
Let's say this some other way. Obviously, in an experiment, your system will stay in one of them. Okay, one. You cannot decide previously, or you cannot know from the beginning where it's going to be. Even if you repeat with the same conditions, it can be in a different place. And that's given by this distribution. What I mean, suppose you have just one realization. Instead of having this distribution, you will have a few peaks here. These few peaks correspond to the minima that you have for your landscape in that realization of your disorder. You only get this when you average over a sampling of. So you don't reproduce with this theory, but that's typical of statistical mechanics. You don't reproduce with the theory the result of a given experiment. You pretend to, or you try to reproduce the result of an average of an ensemble of experiments. What you are not going to reproduce ever is the time average of a given sample. If you do the experiment with your block of something or with your system, you average in time and you get that your magnetization is this. There's only one of the infinitely many possibilities. No, it's not ergodic.
So nothing to do with standard phenomenology.
No, it's not ergodic.
I mean, it's no working.
No, it's not ergodic. You cannot replace. You can never replace time average. So you can never reproduce the average value of one. I mean, of one experiment.
Yeah, but I mean,
The experimentalist has to make samples,
so you
runs.
to the old times of justifying thermodynamics based on statistical mechanics based on microscope behavior through ergodic theory. Yeah.
No, it doesn't
No,
work. No.
Even in statistical mechanics, probably not. Who knows? But yeah,
Well,
that's another thing.
yes. I mean, there are many good results.
Yeah.
You need to, I mean, you know,
Yeah.
It's not generally justified. In that sense, it's the same problem that you find in quantum mechanics. If you just go a little under the carpet, things start to be shaky. It happens. Yes. In statistical mechanics, it's the same problem, and here even you don't have ergodicity, so you cannot predict what an experiment will give you. But a ensemble of experiments. What is the macroscopic in the sense of ensemble of collectivity that you expect? What is the macroscopic or typical behavior that you would expect? Not the result of a given experiment. That's for sure.
So then, from this perspective, our universe is a isostimulus.
From what perspective? From my perspective, or?
Of classes, or universe.
Ah, yes, it's one sample.
Right?
One sample of it can, I mean, yes, I mean there, you know, this is already philosophy, so we'll like this. But this, I read some things about this. Universe is only one single realization of one of the infinitely many possible universe with different constants, different couplings, different particles, different histories from beginning from different initial conditions. If you pick at random the value of Planck constant of coupling, I mean the coupling between forces, etc., you get different realizations. We are living in a glass. I don't know. I cannot talk about that.
So, without changing too much the possibilities of the universe, even for the actual values of the constants, couplings, etc., we understand our universe as a realization of that. Yes. But then the question is, are we living in a glass or in a crystal? No, maybe you can. I have I like it very much. Thank you. It was very clear. It's quite new to me. One of the things that is changing a bit the topic of we have been discussing so far. One of the things that I noticed quite relevant, and indeed happens in many fields of physics, is the simplicity of the power of considering one by one interaction to describe so many things. So I would like to know
if other attempts within this field of complicating the interactions to explain, for instance, little inconsistencies, I don't know, in the way the birds are flying, perhaps instead of considering what is doing the nearby bird, do more over the, is this?
That's a very good question. When I said, a very good question, because it allows me to explain something I didn't say because I was very fast. When I said this model from 1920, basic model I studied in every book in condensed matter and even quantum field theory as the minimal model of interacting systems, describes ferromagnetic and ferromagnetic systems very well. What I mean is describes very well the transition. This point, because at that point things are independent on the details, the critical point. At that point, exactly, the system is a scaling invariant, and it doesn't matter what Hamiltonian you put, as far as it has the same symmetries as this one. You can include here as many terms, as many interactions, 3, this is to 3, 4 spins, long range interactions, quadratic interactions between neighbors, whatever. The most relevant term in the RG group, in the randomization group meaning, is this. And all the properties of the transition are described only by that essential terms in your Hamiltonian. Okay, that's why minimal models are so important. But I think a different thing is that you want to explain the properties of your magnetic system, a normal magnetic system, magnesium, the typical magnetic system, not even a spin glass, in this phase or down here. Then you want to use that for applications, so you want to predict the property, even you want to predict exactly where the critical point is, you need to take into account the details of your Hamiltonian. Whether it's a cubic lattice, hexagonal, what kind of atoms you have, what kind of interactions they have. You have to get as many of those details in this Hamiltonian. That Hamiltonian will describe you the phases better, even where the critical point is, what is the value, because this is say a normalized Hamiltonian where the critical point only depends on J, things like that. So the question is very important. In the near critical points, details are irrelevant, and this kind of models are where they are powerful. This model explains ferromagnetism in the sense that it explains why systems get ordered at low temperature.
So I guess that if you, with this format, you are able to reproduce to understand the behavior of the birds, for instance, because
qualitative,
yes,
in the sense that you reproduce the macroscopic details.
So that
not the fine detail if this bird that this red is moving there instead of there, because you are in one of the many organizations, and globally you reproduce statistically what is happening.
Yes, but I would say that will infer somehow that those living birds are operating at the critical point.
That's another very good question. There are much literature about it. In that case, actually, there are, I mean, this is, I can give a course about this, and it's not enough. This is the critical point. There are systems out of equilibrium, always out of equilibrium. You cannot have equilibrium in that case, that are always critical, without tuning of any external parameter. No temperature, no pressure, no volume, no nothing. They are organized, self-organized to be critical, without any tuning of anything. In those systems, these critical properties, this invariance, or this lack of importance of the details on the symmetries, are relevant, describe globally the system in every situation, because there is no tuning parameters. This is something, this kind of self-organizing systems, self-organized critical systems, were discovered in in 1999 or something like that. And since then, have given lots of literature. So this system, for instance, that you are mentioning, you don't tune anything. So you construct it in such a way that it's self-organizing to the critical point. They are, and that's why there's no.
And that's the reason why the one-by-one interaction is enough for more global details, because by definition they are.
It's in the critical point. There are many systems that I believe to work at the critical point. Brain, for instance, brains. Let me say this because I think it's very interesting. Brains, somehow you have two limits. The limit where the brain is completely random and is wonderful because it has lots of trajectories, so lots of states where you, in principle, could store information, but it's very disorganized, very entropic. And the other case where your neurons will say fire in a synchronous way. So for something like this, a brain like this, all neurons doing this, or a neuron that is just completely random. It happens that it seems that brains, optimal brains, operate at the exactly or close to the threshold between these two behaviors. They are chaotic enough or random enough to have variety, so you can store information, process information, use them, but not too randomly, so they are completely useless. So brain is an example of a system that seems to self-organize by construction, how brains have evolved to self-organize in a critical state, where you don't have to tune parameters, so it processes information in a critical way. This kind of yes. Yes.
Are there studies about how these systems, for example, could respond to some external stimuli? For example, suppose you have your flock of birds, and a bunch of them see a hawk here, and then how that stimulus propagates in time across the lattice, for example. Are there studies about this? Or, for example, in the spin glass, some external magnetic field which depends on time?
Yes, that's another good question. In the case of spin glass, yes, there are many experiments with real spin glasses, I mean materials that are disordered and magnetic. And they have made many experiments to determine what is the effect of a changing magnetic field, etc. And this corresponds to the results are in agreement with the predictions that you can make from the Palisi theory of glasses. I mean, interaction, perturbations in systems is always very interesting. In the systems of birds, I don't know, because I don't know. I guess I'm sure they have done this, either in simulations or even in real, because these experiments are pretty amazing. They really make movies of the movements. They measure every bird, they tag every bird, they follow the trajectories, they take all those data and process all that. So I guess one of the experiments is just throw a stone there and see what happens. See how it propagates the detection of it. Yes, I'm sure they have been doing
For birds, it's not so important, but maybe in neurology or in climate change, these studies.
No, in brains or in neuroscience is very important. It's one of the most important. Actually, the brain actually is just a filter. It gets some inputs and has some outputs. You can study the network as itself, the dynamics, etc. But the interesting thing is how information is processed, how the input is filtered, processed somehow, and what is the response. And there are many numerical and real. In numerical, it's very simple. To put an input as your neurons and see the response of your system. That's very often one of the. But even in experiments, of course, these experiments were. A friend of mine was doing experiments in Israel with a hat, and the subjects, the people have to reproduce tasks in a computer. And they were filming a movie what the people made. and they had a hub with some magnetic or electric inputs, so that they could affect, interfere with the activity of the brain. Okay, and then say, right, draw a cycle, draw two parallel lines, write your name. Well, that was 15, 20 years ago. Nowadays they can imprint or obtain images from your brain. So they can tell you, think of a figure, triangle, circle, square. They can read what you are thinking of. Think of something very intensely. Okay, and from these hats, they can recover the noisy parts of a circle, of a square. I've seen this in papers and in movies, because they film this. So they haven't, I think, well, of course, they are trying to implant things in brains as well. That's maybe not so popular to go and tell in the movies, but I think, I guess, I'm sure they're trying to do this as well. But they can get what you are thinking of. And even more than just abstract polygons or figures, and think, well, actually, there are even moving things with the brain. So a mixture of robotics and neuroscience. So you have an arm, and with your brain, with no touching anything, just with the electrodes in your brain, they are able to move an arm and do some task. The brain learns to operate this robotic arm and do some tasks. So it's really amazing.
I think even more. I think even you can think about a sentence and call it to the computer.
Amazon gives you the next shopping list.
No.
So
I think even more.
that's going very fast. Yes. Thank you.
Antes de que la cierres, bueno, ya está, no da igual.
No sé si
No,
lo cerramos.
no importa, no importa.